Welcome to the third and final video on unsymmetric bending. This is an example problem that we'll go through where we talk about the location of the maximum and minimum stress due to this unsymmetric bending. You can probably intuitively say that it'll be A and E, I'm sure. And we'll also find the location of the neutral axis for this unsymmetric bending. Should be a blast. If we're trying to solve this problem where we've got some moment about this axis right here on this very simple cross section, it's just a rectangle. Well, first off, we don't even have to leap into the equations that we just talked about to be able to say that, well, for sure, the maximum stress is going to be at E, right? This is the right-hand rule. We have tension down here at E and compression at A. That's certain, right? Because when we break it down into its components, we're going to have one rotating like this, which is going to cause the maximum compression about the z-axis is going to cause compression from A to B and tension from a maximum from D to E, and then we're also going to have a component that rotates like this, and that's going to cause tension, a maximum tension from B to E, and a maximum compression from D to A. So A and E are having the same things added together. B and D, we don't really even know exactly what their stress and tension are going to be. They might be in either. We don't really know yet, but we know for sure that A is going to be heavily in compression, as heavily in compression as we can be, and that E we're going to be as tensile as we can be. So right off the bat with this, we know that we want to use, because we want to know about the maximum and minimum stress, we know that we want to use this equation. The stress in the x direction. It's going to be negative moment about the z-axis times our lever arm in the y direction divided by our second moment about the z-axis. Add in our moment about the y-axis times our lever arm in z direction divided by our second moment about y. So we can easily break down this moment. I didn't write down how big the moment is. It's 1600 pound-inches. So, and the angle is 30 degrees. So let's break these down. It's color-coded again. Moment about the z-axis is going to be equal to our moment times the cosine of that angle, which is going to be equal to 1600 pound-inches times the cosine of 30 degrees, which is equal to 1,386 pound-inches. And the moment in the y direction is going to be equal to the moment times the sine of that angle, which in this case is going to be 1600 pound inches times the sine, 30 degrees. And that will equal, 800 pound inches. So now we've got that busted down into their components. We're also going to need our second moments of inertia, right, if we were going to use this equation. And I meant to color code, but I'm not going to retake this. And so, I about z, we've got a rectangle, so we can use 1/12 base times height cubed. So 1/12 about the z axis, it will be, the breadth will be 1.5 inches. I thought I muted that. And the height will be 3.5 inches. And that's going to give us 5.39559 inches to the fourth. And about the y-axis, that's that one, is going to be equal to 1/12. The base this time is going to be 3.5 inches, and the height will be 1.5 inches. And we'll cube that one, and that's going to give us 0.9 844 inches to the fourth. So our stress will be equal to, well, negative moment about the z-axis, yada yada yada, 1,386 pound inches divided by 5.359 inches, that's to the fourth, times our lever arm in the y direction. If we're looking for our maximum, that is going to be a point E, and in that case that's going to be 1/2 of 3.5 down, so negative, and then 1/2 of 3.5 is 1.75 inches, plus the moment about the y-axis we said was 800 pound inches. Divide that by 0.9844 inches to the fourth, and multiply that by our lever arm for that, which is going to be in the z direction. That's going to be 1/2 of 1.5 because we're still going for E, so 0.75 inches, and that's going to give us 1,062 psi for our maximum stress. In this case, we've got a lot of symmetry going on, so we can go ahead and say that the minimum stress would be the exact same. It'd just be at point A, and it would be negative 1,062 psi. Alright, so now we want to know about the neutral axis that will go through, it's going to go through the centroid, point C. C is for centroid. So for that, we're going to want to use this equation, that the tangent of the angle is equal to, well, y over z, yada yada. I don't really care about y over z. I care about it being I over z over I of y, the tangent of 30 degrees. And that's going, oh, okay, I guess I should have put a phi there, right? Oh well. Oh well. So that's going to be 5.359 inches to the fourth divided by 1.9844 inches to the fourth times the tangent of 30 degrees. That gives us just about pi, 3.14, which is the tangent of theta, not theta itself. Let's be careful about that. It's not spitting out, radians. It's spitting out a ratio. So we can say that the arctan of 3.14 is equal to the angle of our neutral axis, which is going to give us 72.35 degrees, which is, noticeably not what we had before, or not 30 degrees from the vertical. Okay. Well, I hope that all made sense. Obviously, you can email me if it didn't. Be safe this week. Or, wait, this is coming up on a Friday. Have a good weekend, but be safe.